Hello Year 11 and welcome to our first video here on differentiation. Settle in, this is going to be a long one. I think we're looking at differentiation by first principles today, and I want to work through a few ideas before we get there. So we've previously looked at add functions, right, and what a function does. It turns an x value into a y value, right? So look, here's some examples of that, a bit of a reminder. If my function of x is 2x squared plus 1, then the function of 0, I replace x with 0, I get 2 times 0 squared plus 1 equals 1. So far so good, yep. Let's have a look at some others. Function of 3, 2 times 3 squared plus 1 is 2 lots of 9, plus 1 is 19. Function of x plus 1, I replace x with x plus 1, so I get 2 times x plus 1 squared plus 1, which of course is 2 outside of x squared plus 2x plus 1 is 2x squared plus 4x plus 3. And here's another one, function of x plus h. That seems a bit weird, but it'll become a bit more relevant later on. So 2 times x plus h squared plus 1 is, oh, my head's in the road there, isn't it? Hey, up here. So I expand the brackets there, x squared plus 2xh plus h squared, and multiply those by 2, gives me 2x squared. Gives me 2x squared plus 4xh plus 2h squared plus 1. Okay, so that's the function of x plus h for this function 2x squared plus 1. So a bit of a review of functions there. Now, a secant. We're into geometry now because we're going to be combining geometry with algebra. So really, we're on the fringes of coordinate geometry here with these things. So, here's another example. A secant intersects the function y equals x squared plus 1 and x equals 2 and x equals 5. We're asked to sketch this function and the secant. So let's do that. My function is x squared plus 1. That's a parabola, concave up. The vertex is at 0, 1. So here we go. There's my parabola, concave up, vertex at 0, 1. And at x equals 2 and x equals 5, right, I've got a straight line, my secant, that intersects the curve at those 2 points. Right, there's my sketch. That's pretty good. It's all labelled. Now, find the coordinates of the points of intersection. We do that by substituting x equals 2 into the function. So 2 squared plus 1 is 5. And again with 5, so 5 squared plus 1 is 26. That gives me the y values. So the points of intersection are at 2, 5, right? 2, 5, and 5, 26. Okay. So those are the points of intersection. Now we're asked to calculate the gradient of that secant. It's a straight line. The gradient is the rise over run. So y2 minus y1, 26 minus 5, on x2 minus x1, 5 minus 2, is 21 over 3 is 7. There we go. Nice enough. Righto. Now, we've talked about secants, let's talk about tangents. They're a bit similar, they're straight lines. They just meet the curve at one point. They just sort of graze it and move on. If, and this idea is kind of important, if the 2 points of a secant are very close together, then the secant looks very much like the tangent at either of those points, okay, when the 2 points of a secant are very close together. Now, the derivative of a function, right, we're introducing this idea here of a derivative, is a rule or formula. It's a function, it's a new function. It's a derivative function that calculates the gradient of a tangent to the function. Okay, it is a gradient function. And we write it like this. If my function is the function of x, then the derivative of that is function prime x. So, here's a function and its derivative. I haven't told you how I got that derivative, but it doesn't matter for now. So back to some function work. Find the function of 2, substitute 2 in there. Right, we get 5. Find the derivative, right? Oh, sorry, find the value of the derivative function at 2. Then I substitute 2 into the derivative function. 6 times 2 minus 4. So, if I'm asked to find the gradient of the tangent to this function at the point where x equals 3, what I need to do is to substitute 3 not into this function, but into the derivative of that function. So the gradient is going to be function prime 3, 6 times 3 minus 4. So a tangent to this function here, which is a parabola, at the point x equals 3, is going to have a gradient of 14. Right? That's what the derivative does for us. The derivative tells us the gradient at any particular point along the curve, or the gradient of a tangent. Now, limits. We're going to do these in a lot more detail in another topic. But to begin with, right, we do need to have a brief understanding of them. Look at this function here, x squared plus 2x over x. What happens if x equals 0? Well, I can't divide by 0. That's a little bit of a problem. So it's undefined at x equals 0. You might think we could factorise and cancel the x's, and we kind of sort of can. We kind of sort of do sometimes, but that's really a slightly different function. Okay, I can't substitute x equals 0 into this function. So let's see what happens very close to 0, because if x isn't 0, I can put other values in there. Right? That's the only restriction on my domain, is x doesn't equal 0. So 0.1 is close to 0. If I substitute 0.1 into there, I get y equals 2.1. If I substitute x equals 0.01, that's getting closer still to 0. I get closer to 2. And really close to 0 here, 0.001, really close to 2. Okay, so I can see that as x approaches 0 from above, right, from the positive side, y is approaching 2. It gets closer and closer to 2 as x gets closer and closer to 0. But we should also look at what happens from the negative side, from the other end. So negative 0.1, close to 2, closer again to 0 from below, still very close to 2, and really close to 0 on the left-hand side on the number line. I get really close to 2. I'm getting closer and closer to 2 on either side. And that certainly suggests to us that the limit as x approaches 0 of this function, it's equal to 2. As I said, we'll do that in more depth in another topic, but for the time being, we need to have this idea that the limit as x approaches 0 of this function is equal to 2. That's what that expression there means, that terminology, that nomenclature, notation. So we can evaluate that limit by factorising and cancelling the x's. Okay, we evaluate not the function but the limit as x approaches 0. Now, the big one, differentiating by first principles. Right, we won't always do it like this, but we will to begin with. So we mentioned before that if I have a secant, right, intersecting a function at 2 points, and the 2 points are very close together, then it's a lot like a tangent. So the 2 points of my secant, the 2 points of intersection, are going to be an x and function of x. Substitute x in, you get function of x. And my second point is x plus h, and the function of x plus h, where h is a small number, which means that the 2 points are close together. So the gradient, y2 minus y1 over x2 minus x1, function x plus h minus function x over x plus h minus x. The x's cancel out there, and I get this thing here. So that's the gradient of the secant. Now, that will become very much like a tangent as h becomes very close to 0. So we end up with this thing here. The derivative of a function is the limit as h approaches 0 of function x plus h minus function x over h. Right, we're going to use this a fair bit. That is differentiating by first principles. Let's have a look at some examples of how we do this. So to find the derivative of 3x, right, we have the limit as h approaches 0 of, remember we replace x with x plus h, right, so 3 outside of x plus h, minus the function of x over h. Expand those brackets, we get 3x plus 3h minus 3x over h, cancel the 3x's, we get 3h over h, cancel the h's, and we get 3. And if I substitute h equals 0 into that, of course, I still get 3. Now, sensibly, this function here, function x equals 3x, is a straight line. And so it has a constant gradient, right? It has constant gradient, and if we think, y equals mx plus b, the gradient is 3. So there we go. We have a formula now and not a very helpful one, to find the gradient of this function at any point. And at any point, for any value of x, the gradient is equal to 3. Right, because it's a straight line. We won't do many more of those when we're differentiating. But here we go. Now I have a parabola, right? And this has a changing gradient. So the derivative is the limit as h approaches 0 of, replace x with x plus h. So I get x plus h squared plus 5 x plus h minus 1 minus function x over h. So we replaced x with x plus h, right, to get this first part, and then I subtract the function divided by h. If we expand that out, x squared plus 2xh plus h squared is this part here, 5x plus 5h is here, minus 1. Now be careful here when you distribute that negative to this second term here. So I get negative x squared minus 5x plus 1 over h. Now we tidy up by collecting like terms. The x squareds cancel out, the 5x's cancel out, the 1's cancel out, and I'm left with 2xh plus h squared plus 5h over h. Okay, pause if you like and follow that along. Now I'm going to factorise the numerator there, take the h's out and cancel. So now my limit, now my derivative, sorry, is the limit as h approaches 0 of 2x plus h plus 5. Now I can substitute h equals 0 into that because it's not causing me any grief dividing by 0. So I get 2x plus 0 plus 5 is just 2x plus 5. So the derivative of x squared plus 5x minus 1 is 2x plus 5. Now I'm talking fast, but this video is going to get way out of control otherwise. Feel free to pause, review, rewind, watch it again, comment, like, subscribe. Righto. Now, gradient. Calculate the gradient of the tangent to this function when x equals 2. Remember, that means find the derivative and substitute x equals 2 into the derivative, right, which is our gradient function, our formula for calculating the gradient, if you like. So we start by function of x plus h. So replace x with x plus h. So I've got to square it, multiply it by 2 minus 5, minus the function over h. So we expand that out. Now we tidy that up again. The 2x squareds cancel out, the 5's cancel out, and I'm left with 4xh plus 2h squared over h. Factorise the h's, get rid of them, and I'm left with 4x plus 2h, and I can substitute h equals 0 now because it's not the denominator anymore. And I get 4x plus 2 lots of 0 is, of course, just 4x. So my derivative is 4x, and that means the gradient of the tangent at x equals 2, I substitute 2 into that. 4 times 2, so the gradient is 8. There we go. So there's a fair few steps there. You can probably cut a couple of those out along the way if you like. You don't necessarily have to show all of that working. And a reminder, we're not always going to do things like this. There's a shortcut. But that's the working in full, I like to think. Righto, that's it. It has been a bit of a marathon there. And I have been talking pretty fast, so feel free to rewind or slow it down, pause, do some of the working out yourself and make sure you arrive at the same answers. But here we go, this is what we covered. A secant, straight line that intersects curves in 2 places. And a tangent is like that, but it just meets the curve once, it just scrapes past it. The derivative of a function is a rule or a formula for calculating the gradient of the tangent at any particular value of x. We write the derivative, right? The notation we use is function prime x, or it is for now. We use limits to look at the properties of a function very close to an undefined point, and we use limits for calculating the derivative like this. Okay, that's our formula for calculating the derivative of a function, right, by first principles. Okay. Function x plus h minus function x over h, the limit as h approaches 0 of that. Okay, righto, that's it. If you've got any questions, and you very well may, jot them down so you don't forget what they were, and make sure you ask your teacher. Okay, thanks very much. Next up, we'll be looking at a rule for differentiating powers of x. This is going to be shorter and easier, and you'll be so pleased to know what it is. Look, I know I'm really selling it there, but I think you'll appreciate it. Okay, see you in class.